Okay, good morning. So we're going to start the third day of the GFD session. So this morning we're going to have Alexa Griesel from University of Hamburg. So she's going to tell us some aspects of mesoscale, meso to submesoscale turbulence. Okay, over to you.
Okay, thank you. So hi, good morning. The subject meso to submesoscale turbulence, it's quite a big area, and we have already heard aspects of it already in some talks. So I'm also only going to talk about some aspects of this field, and I'm going to focus on actually using diagnostics from Lagrangian particle trajectories. And I've also listed the people that I've been working with on this subject, so I want to acknowledge them. Okay, I'm going to start with basics. So let's compare atmosphere and ocean again. So the atmosphere is compressible, whereas in the ocean, the Boussinesq approximation is quite a good approximation. So, of course, in the atmosphere, we have the equation of state with H2O in 3 forms. And in the ocean, of course, we have salinity. So the Rossby radius in the atmosphere is usually really well resolved. Whereas in the ocean, the Rossby radius in climate scale models is very small compared to the atmosphere, and it's usually badly resolved. So I want to also stress that in terms of dynamical regimes, in the atmosphere, you have the synoptic scales. This is where the weather takes place. And in the ocean, these would be called the mesoscales. And in the atmosphere, then the subsynoptic scales would be called the mesoscales, which in the ocean then in the same dynamical regime become the submesoscales. So sometimes this can be a little bit confusing. So in the atmosphere, density and heat capacity are very small. In the ocean, they are very large. And in the atmosphere, you have mountains. In the ocean, you also have topography, of course, but the distinction is that you have closed ocean basins. So the atmosphere can be considered as a heat engine, whereas the ocean is actually mechanically driven by winds and tides. Okay, so you are all very familiar with the linearization methods here, but I want to just start with a world in which you have no turbulence. So you have the Navier-Stokes equations, and then you linearize them, and then in the ocean, so this was, okay, so this was also already shown by Carsten on Monday. Then you get your ocean linear wave solutions. So this is a frequency wave number diagram where you have the Rossby waves, you have the internal gravity waves, you have the surface gravity waves. And then if you also have this compressibility term here in your equations, in the ocean you also get the sound waves. But dynamically they are not important. So with the Boussinesq approximation, of course, they are eliminated. So So in the linear world, basically those waves that exist kind of next to each other, and they would have quite a boring life without ever really knowing about each other. So life gets more interesting when this little devil, the advection terms, come into play. And so in a Reynolds decomposition, then of course you get your eddy fluxes. And if you then look at the kinetic energy equations, then you arrive from this advection term here at the spectral kinetic energy fluxes. This would be in spectral space. But then you also, in space scale, you can also look at a coarse-grained flux. So we have already heard a lot about the definitions of the meso and submesoscale regimes, but I'm going to repeat it here. So what is oceanic mesoscale turbulence? So those are geostrophic eddies, so cyclones and anticyclones, typically in the ocean radii of 10 to 100 kilometers. The ocean equivalent of the storms in the atmosphere. It drains energy from the mean flow by barotropic baroclinic instability, characterized by small Rossby number, and can be described by the QGPV equation. So what you see here is a typical diagram of the Lorentz energy cycle in the ocean. So this is actually a view that can be seen as an integral over the whole volume of the ocean. So here you have the main pathways that create the eddy kinetic energy. So here would be associated with barotropic instability. And here you have your baroclinic instability pathway, and this would be related to Ekman pumping. So I want to mention here just a few differences to the atmospheric Lorentz energy cycle. So if you diagnose this and put numbers on all of these terms, then the first thing to note is that those conversion terms relative to the forcing and dissipation terms in the ocean are actually smaller than in the atmosphere. So in the atmosphere, those conversion terms are, relatively speaking, more important. And then diagnosed in this volume integral, you also get actually a change in the direction of these arrows. So in the atmosphere, usually this arrow goes from mean potential to mean kinetic energy. And in the atmosphere, this term goes actually from the eddy kinetic to the mean kinetic energy. Whereas in the ocean, it's the other way around on average, where it's associated with barotropic instability. But if you actually, of course, look locally at the energy balances, then there are also going to be transport terms that mess up your picture a little bit. So if you want to locally diagnose those terms, then it gets a little bit messy because you also have the transport of the energies in there, right, that don't play a role in your global integrals. And so what you see here is an example of a diagnostic of these conversion terms. So here in the upper part, it's transfer from EPE to EKE. And so you see that you don't only really have positive terms, but locally they can also be negative. And then the same in this barotropic instability term, locally they can be also negative. So now submesoscale turbulence, we have also already, I think we've seen exactly this picture here. So what usually it is defined with respect to dynamical regime. So flows with Rossby and Richardson numbers order 1, not governed by QG, ageostrophic components become important, sharp fronts, stronger vertical velocities. Sometimes in papers you also read it as a definition with respect to scale. So horizontal scales of 0.1 to 10 kilometers, vertical scales of 0.01 to 1 kilometers, time scales hours to days. One has to be a little bit careful though then with this definition, because these scales can contain both, so could also still be mainly geostrophically balanced. So here you see an example from a paper by Su et al. From this, it's quite a famous, actually now global high-resolution model simulation, the 148 MIT GCM simulation. And so typically what you see, so this is vorticity in the Indian Ocean. In the winter, you have this enhanced Rossby numbers. So submesoscales, of course, they feature flatter spectral slopes and a tendency for forward kinetic energy cascades. And there's going to be a little bit more on that in the part 2 after the break. Okay, just a little bit of this introduction, and I know some of you are much more familiar with turbulence theories than I am, but so I'm still wanting to mention those two paradigms of turbulence. So we have 3D turbulence, where forcing and dissipation scales, so they are well separated in theory of this inertial range with the k to the minus 5/3. Then you have the 2D turbulence, of course, where you have your injection scale, energy and entropy with your inverse cascade and your forward entropy. In QG, you have similar invariance and inertial ranges in theory, but now you get also potential energy and baroclinic modes. And so sometimes these submesoscales are then postulated to bridge the gap between the QG and 3D turbulence. In reality, of course, we know that often this energy input here is spread over a large vicinity of Ki, so you don't get really inertial range. And forcing dissipation scales, especially in the ocean, are very close together. And then you can also have wave interaction across the ranges. And then homogeneity and isotropy assumptions are also often violated. So insight has come in also from 2 layers. So insights about the QG turbulence has come about with looking at just 2 layers. And this is textbook, basically. So the idea is then that now you also have baroclinic modes, right? So here there's going to be at close to the injection scale here, there's going to be a conversion of the baroclinic to barotropic modes. And it is the barotropic modes that actually then do the inverse cascade, but the baroclinic energy goes to small scales. So on scales larger than the Rossby radius, there's a direct cascade of baroclinic kinetic plus available potential energy and an inverse cascade of barotropic energy. And on these smaller scales, then the layers interact only weakly, and they behave more like 2D turbulence with an entropy cascade regime in k to the -3 scaling with the baroclinic energy. But here also, this doesn't take place at just one wave number, but it's also spread over a range of wave numbers in reality. So observations. So I'm sure that many of you who knows this picture of, it's a famous picture of Scott and Wang. Anybody knows this figure? Okay, so this is actually, so it is very difficult to diagnose the inverse energy cascade, kinetic energy cascade from observations, because you need really good resolution of the data, and it should be gridded. And so this is a famous example by Scott and Wang, and there was also some work about this actually by somebody from this institute. And so what you see regularly is this inverse cascade for small wave numbers. So this is usually diagnosed. And so you use geostrophic velocities that are diagnosed from SSH gradients. And so there has been then some arguments about, since the SSH actually represents the baroclinic mode, so you shouldn't maybe see an inverse cascade going in the baroclinic mode. This was kind of resolved by Scott and Arbig. It is my understanding at least. So they have a 2-layer model. So if you allow for different thickness of the layers, then there also can be baroclinic self-interaction, and there can also be an inverse flux of baroclinic kinetic energy that is actually sometimes even dominating the barotropic flux. And then there was also some debate about this downscale flux here, because you could argue that from the geostrophic velocities, you wouldn't expect a downscale flux. And so it is probably due to an inadequate resolution of the altimeter. So progress is expected from the SWAT mission that will, it's altimeter data that will lead to, are currently ongoing and will lead to much higher resolution of these SSH fields. Okay, now who knows this picture? The Nastrom gauge spectrum in the atmosphere. Okay, so this is also a famous example of the atmosphere. So it is the spectrum of kinetic energy and also actually potential temperature. So for synaptic to mesoscales. So mesoscale to submesoscale equivalent regimes for the ocean. And so what you find here is really this k to the -3 spectral slope. So that kind of basically agrees with your geostrophic turbulence of an entropy cascade. So this is a proof that this entropy cascade is taking place in the atmosphere. And then here you find actually for larger wave numbers, you do find this k to the -5/3 slope. So this would be the mesoscale, so oceanic submesoscale regime. And there is, as far as I see, there is still no clear understanding which processes really produce this slope, but it is associated actually with the forward cascade and probably something like stratified turbulence. So I'm going to talk about the ocean and this regime in the second part of this talk more. Okay, in the remainder of this first part now, I'm actually going to focus more on stirring by mesoscale eddies. And I'm just going to show you an example of the effect of isopugnal diffusion on ocean circulation. And then I'm going to talk about really classical diagnostics of Lagrangian diffusivity and how I have applied them. And in the part B, it will then be about observations. So what could we learn from observations, and particularly in the South Atlantic from the Benguela upwelling region, about the meso to submesoscale turbulence. Okay, now in the tracer equations of an ocean model, you parameterize the effects of eddies, usually with an isoneutral diffusion tensor. So this is your eddy flux, and this is your mean gradient, tracer gradient. And so this is a tensor. So it has two parts, essentially. So there's an antisymmetric part in this tensor, and it represents the advective properties of the eddies. So instead of writing this actually as the antisymmetric component in the tensor, you can also put this on the left-hand side, and it's equivalent. You can also write it as an advection velocity, and then it appears here as like a U star, and then this U plus U star will be called your residual circulation. So, but it is actually numerically more stable if you represent it in ocean models and at this antisymmetric component. So this is equivalent to the GM parameterization, and the effect of this is that it kind of wants to simulate baroclinic instability with the GM coefficient, and the effect is the flattening of the isopycnals. But then we also have isopycnal diffusion of tracer along isopycnal. So this represents then the symmetric part in this isoneutral diffusion tensor, and it is a true eddy diffusivity. It leads to destruction of tracer variance along isopycnals, basically, and it is the ready coefficient in ocean climate models, and it mixes along isopycnals. Okay, so there have been many studies about the GM coefficient, and it's pretty obvious to see that, so the GM coefficient leads to a flattening of the isopycnals, so it leads to a decrease in the density gradients. So many studies have shown if you increase your GM coefficient, you decrease the overturning circulation, you decrease the Antarctic circumpolar current. And yeah, so with the isopycnal diffusion, on the other hand, there have been many studies focusing on tracer uptake. So you can imagine that if you have a gradient of, say, anthropogenic carbon along isopycnals, so this anthropogenic carbon, it will be higher at the surface. So if this diffuses, then with this diffusivity along isopycnals, it will draw more of this tracer in, and it will then increase the fluxes at the surface. So this is one example of a study. So they found there's a 15% more carbon uptake with increasing this isopycnal diffusivity sixfold. And then the effect on temperature is actually maybe not as straightforward, but there was a study, for instance, if you have a 4 times CO2 scenario, then isopycnal diffusion leads to a warming to changes in the isopycnal temperature gradients along isopycnals. Yeah. Okay. So, but ocean circulation, so this is actually diffusion along isopycnals, right? So to first order, so it should not in the ocean interior, if you are not exposed to the surface fluxes that could change your density, then it should not change the density gradients, right? So it's isopycnal diffusion of temperature and salinity, unless, so it shouldn't change your density gradients unless there is actually an effect from the nonlinear equation of state. And so we have investigated this a little bit further. So we have increased the isopycnal diffusivity, and then we can see that actually the Antarctic circumpolar current, it drastically decreases from 150 sweardrops to 108 sweardrops, and the overturning circulation also decreases from 21 to 14 sweardrops. So what you can actually see in the temperature difference, so there is a cooling predominantly around those 40-degree, so equatorwards of the 40-degree latitudes, and there's also a freshening. So the effect on salinity is there is a freshening equatorwards of those 40-degree latitudes. So if you look at the effect of temperature and salinity on these density differences, so you can see that actually, so this is the total, so this is actually the effect of temperature. So you see here that the effect of temperature is that this gets denser, and the effect of due to salinity is that since it leads to a freshening, so this density here gets smaller. So the combined effect using the model in the model linear equation of state, you see that the net effect is temperature winds, and the net effect is the densification here, which actually then leads to a decrease in these meridional density gradients. So you can also diagnose the density difference with the linear equation of state, and you don't see that much difference. So you can look a little bit in more detail at the isopycnal fluxes. So here you have the tendency of temperature. Here's the advection term. So this is the divergence of the isopycnal diffusive flux. Here's also the GM flux, which has not changed because we have not changed the GM coefficient. And there's also vertical diffusion. So what you see actually is increasing the isopycnal diffusion. So here you see the meridional isopycnal flux of temperature. So you see it is actually poleward north of these 40-degree latitude, and it's equatorwards here. So it leads to an increase in the meridional isopycnal fluxes. And so the effect of temperature is then the divergence is this. So the gradient is equatorward. And so this leads to a predominantly cooling and freshening equatorward of 40 degrees north and south. And when you look at these two together, then temperature wins. And and this is because actually in most of the oceans, we have a so-called alpha ocean, where density is determined by temperature, so your expansion coefficient alpha. And only like in the polar latitudes, it is a beta ocean, where it is determined by salinity, at least below the mixed layer. As a quick summary of this part, so we find a surprising importance of actually also isopycnal diffusion for the ocean circulation. So we see an increased poleward diffusion of heat and salt, and that it is actually the surface heat and freshwater fluxes that react by pumping cold and fresh water then into the interior. And this leads to a cooling and freshening equatorward of 40 degrees and temperature winds. And so the net effect is a decrease in the meridional density gradients. And so it's easy to see that this then leads to a decrease in the ACC transport, but you also decrease the meridional density gradient in the northern Atlantic Ocean, say. So it's not, so the MOC also decreases, so it's not as straightforward as with the ACC, which is a zonal current. The MOC is a meridional current, how this is exactly related, but this is another subject. So nonlinearities of the equation of state, we think only play a minor role. Okay, so now I want to move to diagnosing the eddy diffusivities. So we have one classic method. So it's the Taylor diffusivity. So we look here at single particle diffusivity. So we look at the displacement of the particles from the initial position for single trajectories. And then the diffusivity is half the time rate of change of this mean square displacement, right? And if this grows linearly in time, then we have a diffusive process. And so this can also be written as the integral of the velocity autocorrelation. And yeah, here you see some actual trajectories of an eddy resolving ocean model. And what is typically happening is you do not get this decay of just a decay of the velocity autocorrelation, but it actually oscillates. And this is due to the rotational parts of the eddies. And then your diffusivity from those single trajectories looks like this if you integrate it. And then, of course, you have to have a number of particles to average over. And okay, so to actually have the diffusivity in the diffusive limit, so you take this integral to infinity. In reality, you have finite time lags, so you have to have long time lags. And then you can actually also write this diffusivity as a product of the eddy kinetic energy and a Lagrangian time scale. This is the integral of this kind of normalized a velocity autocovariance. So it's also called Lagrangian integral timescale. Okay, now here we have some examples of trajectories in the Southern Ocean. They were deployed, millions of trajectories in the whole ocean, actually, of a global eddy resolving model. And here you see a few trajectories at different depths south of Australia. And you see there are the eddies, and there's also some topographic steering going on. So we want from these trajectories, we want to then diagnose the diffusivity. And so here are already a couple of examples. So you see here in color the mean flow, and you see some of these trajectories in the South Atlantic. And so there are two boxes here. So one box is where you don't have a strong mean flow, one box where you have a strong mean flow. And then when you diagnose this diffusivity, you actually see that in this area, you have a decrease of diffusivity. So first of all, it does converge with time lag, but you need at least 40 days. And so you do see a decrease of this eddy diffusivity, which is consistent with a decrease in eddy kinetic energy. But if you actually diagnose it with this really strong jet present, then you see that these diffusivities are much more close together. And in fact, the diffusivity at the surface is smaller than the ones at depth. And so this is due to this suppression of mixing in the cross-stream direction. So actually here, so the diffusivity, yeah.
So how sensitive this is with the wind forcing, like surface winds?
Wind forcing?
Yeah, if we continuously blow the winds, so how sensitive they are?
Yeah, I mean, I haven't done this experiment, but there are a lot of experiments. It depends on what kind of model you're using. So if you have a very coarse model where you don't resolve the eddies very well, then you will, yeah, it's actually a good question. You have a competition between eddy kinetic energy and I mean, there's this debate on how much. So if you increase the Southern Ocean wind stress, right, you get higher eddy activity, but you also get larger mean circulation. So there is this eddy compensation effect going on, maybe. And so you would expect in these coarser resolution models, I think, an increase in the eddy diffusivity if you diagnose it like this. But it depends if you have how much your eddy compensation.
The model resolution. So let's say there are like 110-degree model and one is a 1-degree model. So like which model will show the uptake of the heat in terms of the eddy diffusivity, like the larger uptake of the heat?
Well, it depends on your kappa then, right? So in your 1-degree model, you don't have eddies. So so you basically all your eddy effects are parameterized. And then it depends on what kind of kappa you're choosing, basically. And so, and it is actually what we want to do with these eddy resolving models. We want to diagnose this kappa, right, so that we can get the heat uptake and the carbon uptake right in those coarse resolution models so that we know which kind of kappa to use, right? Was that your question? I'm not sure.
I had a question as well. For the time lag up to 120 days there, do the particles stay in the box that long? I mean,
Yeah, that's the problem.
Okay.
It's a non-local diffusivity. So diffusivity is non-local. And that's how it is. And so I am using trajectories here that pass through this box. So they do not stay in this box entirely, no.
And you keep integrating after they leave the box. Okay.
So if you average, it gives you somewhat of an averaged kind of smeared out picture. But yeah, this is how diffusion works. Yeah, and so there's also, so eddies have a large rotational part, right? And so let's assume you just have this kind of trajectory or you have circling trajectories in this way, then if you integrate this, then your diffusivities actually would lead to no net diffusion, right? Then you would just have an oscillation of your velocity autocovariance. And if you integrate this, it would integrate to zero. So there is a large part of these eddy fluxes that is sort of non-diffusive. And this is one of the reasons also why you need these large time lags to integrate over these rotational parts. And this is also why you're getting this maximum here. Sometimes people take this maximum as the diffusivity, but this is not the true diffusivity. This is kind of related to these rotational parts, to this increase in diffusivity, and then it decreases again. But if you have an eddy field with many different kinds of eddies, then this diffusive limit gives you the actual diffusivity. Okay, I think I'm actually slower than I thought it would be. But so I want to connect now this Lagrangian diffusivity to PV diffusivity that's diagnosed from quasi-geostrophic linearized theory. So we've already seen this QGPV equation. So here you have a mean background current and a stratification. It depends on depth, and you have your eddy PV. And now we're assuming in some, like a WKB kind of sense, we're assuming locally horizontally homogeneous conditions. So we're assuming that this velocity, this horizontal velocity and also the stratification, they vary slowly horizontally. So then this becomes just an eigenvalue problem that you can solve locally for an n and a u that depends on z. And then you can actually predict the eddy, PV, and buoyancy fluxes. So you can predict them so then you can solve numerically, and it gives you this vertical structure function. And then you also have your k's, wave numbers, and frequencies. It gives you stable and unstable modes. And so what we're using is the properties of the most unstable mode. And so you, as a solution, you actually get the buoyancy flux and the PV flux. And the diffusivity is then from the projection of this flux across the buoyancy contours or across the mean PV contours. And what this turns out to be is, and I'm today only going to focus on this one here. So what this turns out to be is you can write this then. So this becomes EKE, where you have to actually assume some things about this amplitude psi 0, but this is the eddy kinetic energy that would be sort of predicted from your linear stability analysis. And this actually becomes this well-known effect of the steering level. So it gives you a mixing enhancement. So this is the growth rate of your most unstable wave. And here is your mean flow. And this is the phase speed. So this is actually the intrinsic frequency. So this intrinsic frequency becomes 0 when n dot u equals the phase speed of your waves. And the diffusivity, so if you don't have an unstable wave, then the diffusivity would be of 0, right? So the diffusivity is enhanced at the steering level. And otherwise, it would be with a strong mean flow, it is suppressed. So you can write this also as this product of eddy kinetic energy, and this can be considered like a length scale. It has the dimensions of time. And now we can actually compare this to quasi-linearized Lagrangian diffusivity. So we're assuming that I have here my Eulerian eddy velocity, and then I'm assuming, and this is sort of the linearization, that my eddy velocity at time tau for a drifter that was at time 0 at point x, I'm just saying it will be advected by the mean velocity just, and this is the linearization. And then from this, using also this, you can calculate the velocity autocorrelation. And then it turns out that this integration leads to EKE times the cosine of this function. So you again have this difference here. And then, of course, if you integrate this velocity autocorrelation, then it would go to 0, except where n dot u equals c. So we are introducing a decay in the velocity autocorrelation. And this actually produces then your diffusivity. And what it turns out then, so we are having, and we have already seen earlier, right, that your diffusivity, it kind of has a decay, but it also oscillates. So this is nicely captured by this equation. And if you integrate then this, then you arrive at this expression, and then you actually see that it matches your prediction, what we have just saw from the PV diffusivity. So this Lagrangian decay scale kind of becomes your omega, so your growth rate. Yeah. So now what we can do, and I'm running out of time, unfortunately, is we have a diagnostics of Lagrangian diffusivities actually from the trajectories in the model. So we can estimate, for instance, those decay rates from the velocity autocorrelations, and it is kind of a way where we want to see if we can use a parametrization that is based on this diffusivity in the ocean. And okay, so I'm just going to show you now just a quick results. So here is the eddy kinetic energy diagnosed in the model, and this is just from a time mean. You can also compare this actually to the amplitude of eddies that are tracked in the model, coherent eddies. Of course, there are no coherent eddies in the tropics. And you see, though, that this otherwise it matches pretty well the patterns. The EKE from the linear stability analysis, on the other hand, it doesn't include the advection. And so it is very localized, of course, because it assumes that locally you have the instability and that it goes directly there into the mixing. And so you have a localized EKE. And here you have basically, you can also diagnose the distance traveled by these eddies. So they travel here in the ACC. They are advected by this ACC zonally. Otherwise, they go, like Rossby waves should go westward. So they travel at times more than 300 kilometers. And now you can diagnose this time scale. And so this is your Lagrangian integral time scale. And it also, so you see here that this mixing suppression in the ACC and in the western boundary currents, and an enhancement on the equator with flanks where you do not have this mixing suppression. And the time scale from the stability analysis also shows a similar pattern at least. So let's look at the depth dependence. So first we actually have to note that the Lagrangian diffusivity in zonal average diagnosed from the model, it looks completely different from the PV diffusivity diagnosed, basically predicted from the stability analysis. And so we can explain this by basically the eddy kinetic energy in the model decreases more rapidly with depth than the diffusivity that is predicted by the linear stability analysis. Because, right, this diffusivities here, both they are a product of this year and this year, and this year and this year respectively. So this is the time scale. So this is the Lagrangian integral time scale. So here you see again this mixing suppression that is nicely seen in the time scales. But if you multiply this with this enhanced eddy kinetic energy, you get a more rapid decay and you do not get this steering level effect. So a summary for this part. So the differences between the linear PV diffusivity and the diagnosed Lagrangian one arise from differences in the eddy kinetic energy. And also actually, I've kind of skipped that, but I want to show this right quick. So I have said that you can also diagnose the Lagrangian decay scale, right? And in equations, it should be similar to the growth rate of the eddies that is diagnosed from the linear stability analysis, which is shown here. And this is the Lagrangian decay scale that you diagnose from the trajectories. And so you see the patterns are similar, but this decay scale is actually 4 times this growth rate. And it is also depth dependent. So the summary is, so the differences, so there are large differences, but they can be explained by the differences in the eddy kinetic energy and gamma versus omega I. So there is actually no significant overall enhancement of mixing at the steering level because the EKE decreases strongly with depth. And so it is, even though there are large differences, you're not lost here. You can still base a parameterization on this prediction from linear stability theory if you use just a proper EKE, and you can, there are ideas on how to use a prognostic model for this eddy kinetic energy. And then you have to also make some modifications to your growth rate. you have to use a larger growth rate and a depth dependence. And I am finishing with this example of observations of diffusivities. So there's not many observations of depth dependence of these diffusivities at all. So there's like two main examples of the nature survey. It's in the eastern subtropical Atlantic, and then there's this DIMES project, Southern Ocean, west of Drake Passage. And so you see, so some of these are direct mixing estimates, these points, and some of these are actually more indirect. And so you see there's a wide variety of also depth dependence, even for these locations. So there's more work still to do. So thank you for this first part, for listening.
So for time reasons, maybe we can have just one or two questions, if there's any burning questions. David?
The linear stability analysis disagreed with right at the end of your talk with the observed diffusivity. Is that just because the model doesn't resolve the linear instability at depth, due to vertical resolution or something like that?
Well, I mean, I was only showing like a zonal average. So there are some locations where you still see this steering level effect also in the model. So I don't think it's about that. I mean, I think, so in the DIMES region, there is also only like a slight, so from observations, you also don't necessarily always see, I think, the steering level effect. And even in the DIMES regions, it's not very, how you say, exposed.
Okay. And from a little bit earlier in your talk, you had the surprising effect of isopycnal diffusion, and I think you mean with not counting for the bolus effect. But why is that? Just because the isopycnal diffusion changes the surface temperature and therefore the buoyancy forcing?
Yes.
Okay, thanks.
So sorry, minor follow-up on that. So we did some stuff. If your GM ends up being state dependent, then you have these kind of positive feedback loops. So your isopycnal diffusion can really change the stratification through the GM case as well. So then you have a really big change in the kind of ventilation pathways and rates as well.
Yeah, so this in a feedback with the GM coefficient is also interesting, yeah.
One more from Kasten or some Manita.
Thank Alexa first.